Well, good morning. What a wonderful event to be at. Energy is prosperity. Energy is how we make things. Energy is how we move things. Energy is how we warm our homes and prepare our food. Energy is prosperity. Over the last century and a half, a subset of the planet of this a population of this planet learned how to harness a legacy resource of fossil energy and created prosperity the likes of which have never been seen on planet Earth. But we know now that that bargain was Faustian. The use of that fossil resource produced greenhouse gases that today threaten to make our planet uninhabitable. Today I want to talk to you about how we got to this point in time, and more importantly, how we can move forward. How we can move forward and how we can't move forward with the most important challenge of our time. How to sustainably provide energy and the prosperity that comes with it for the entire planet. If you lived in America in 1830, you were probably involved in agriculture, because in 1830, 70% of the American population was involved in agriculture. And that work was backbreaking. An acre of wheat took 56 worker hours to farm and produce just 15 bushels. Your day began at dawn and it ended at dusk. There was no artificial light. Your heat came from wood. Your transportation was by animals. If you didn't emigrate, you probably never traveled more than 50 miles from where you were born. Artificial light was arguably society's greatest need at that time, and by the early 19th century, whale oil had emerged as the source of choice for that light. But by 1850, whales are becoming scarce. They've been overhunted. Whalers have to travel ever farther to find whales. The price of whale oil becomes too expensive. A new alternative is needed. Already by 1846, Adam Gessner, a Canadian geologist, had demonstrated that he could extract a material that had almost ideal properties for light from coal. And he called that kerosene. But production was problematic. You couldn't get enough of it. And so it wasn't practical. In 1851, Samuel Martin Cayer demonstrated that a very similar material could be extracted from oil, and he started selling his product as carbon oil. The last piece of the puzzle that was needed was a source of oil. Oil seeps had been known in Pennsylvania for a long time, but in 1959, the first well was drilled near Titusville, and the rush was on. John Rockefeller was involved in the production of oil almost from the very beginning. In 1870, he reorganized with his partner J.D. Flagler as Standard Oil, which rapidly became the largest company, first in America and then in the world. Almost from the very beginning, a powerful relationship emerged between per capita GDP and per capita energy use. Access to artificial light changed the world in ways that today are difficult for us to imagine. In 1850, the average person used about 5 kilolumen hours of light per year. Today, the average person uses about 60 megalumen hours of light per year, a 12,000-fold increase. With access to artificial light, the workday lengthened, productivity increased. Improvements in diets and preparing food led to better health. Slowly but surely, these changes began an inexorable rise in prosperity. In the second half of the 19th century, oil was still used primarily for light, for kerosene. And what we call today gasoline and diesel were mostly a waste product. A number of researchers had been experimenting with the idea of electric light. But in 1879, Thomas Edison illuminated a carbon filament inside a high vacuum. Electric light was a practical reality. Kerosene prices plunged. But other innovation was on the march. In 1908, Ford produced the first Model T, introducing, for the first time, practical, affordable, gasoline-based transportation. By 1914, a Model T took only 93 minutes to assemble on a Ford line, and only 20 years after its introduction, 18 million were registered in America. In 1903, the Wright brothers flew a Kitty Hawk, introducing an entirely new form of transportation. Again, dependent on oil. And in 1927, Lindbergh crossed the Atlantic, shrinking the globe, shrinking the distance between continents. In a period of just 30 years, transportation had been transformed forever and to modes entirely dependent on oil, on cheap, abundant energy. Those trends only accelerated as we move forward. We said in 1830, 70% of the American population was involved in farm labor. By the turn of the century, that number was just 41%. And at the end of the Second World War, 7% of the American population was involved in agriculture. That acre of wheat that used to take 56 hours to produce 15 bushels now took 3 hours to produce 31 bushels, a 50-fold increase in productivity. If you lived in America in the middle of the 20th century, you were probably involved in manufacturing. Artificial light allowed you to control your day rather than your day to control you. Your heat came from oil or coal, and you traveled by car. The construction of the modern highway system enabled vast migratory trends and opened the entire continent to development. Those trends only accelerated as we moved through the second half of the 20th century, as the possibilities afforded by cheap, abundant energy became ever more clear. Today, less than 2% of the American population is involved in agriculture, and the United States ranks in the top 3 in more than half of all agricultural commodities. In 1980, 6 of the top 10 companies globally were oil companies. It's an extraordinary story. Real per capita GDP rose by 5-fold over the course of our story and by 10-fold over the course of a century and a half. An extraordinary change. But there are challenges on the horizon. The use of that fossil energy produces greenhouse gases that lead to a rising temperature. The last time the surface of the ocean was as warm as it is today was 120,000 years ago, and sea level was 25 feet higher than it is today. The average elevation above sea level of London is 35 feet. The average elevation above sea level of Miami is 6 feet. 25 feet of sea level rise would submerge 9 of the 31 cities with more than 10 million people globally. If you melt every scrap of ice on this planet, how much does sea level rise by? 220 feet. The elevation above sea level of Tokyo, 131 feet. More than 2/3 of those cities with more than 10 million people would be submerged, and on the order of 1/3 of all humanity would be displaced. Together, clearly, these developments mandate the development of a new energy system. The scale of the challenge before us is extraordinary. Remember that with only 5% of the world's population, the United States is responsible for 20% of global emissions. But that makes sense because the United States is 25% of the global economy. 10% of the planet has no access to energy at all. Another 10% has only intermittent access. 3.5 billion people, half the population of this planet, lack access to clean energy for cooking. The challenges are enormous. Raising these people from poverty and providing energy will more than double energy demand by the end of the century. But it's the greatest challenge of our time and one that we really have to accept. And we have to accept that we're going to have to do it across 200 countries with every conceivable manner of governance. As we talk about how we might do that today, then, we have to remember the ground rules. And the ground rules are these. First, energy is prosperity. And the entire world has a right to the same level of prosperity that the OECD world enjoys today. The second, 85% of all of our energy today comes from fossil fuels. And the third, global energy demand will double by the end of the century. Well, against this backdrop, as you heard, in 2015, Breakthrough Energy was created. By now, Breakthrough Energy has supported 165 companies across all 5 areas that we invest in: electricity, transportation, buildings, manufacturing, and agriculture. When we were together last, 18 months ago in Seattle, I talked about some of the lessons that we'd learned over the first 5 years at Breakthrough Energy. Today I want to do something a little bit different. Today I want to look forward. Today I want to talk about how we're going to address this challenge of providing the world clean energy. I want to talk about things that could work and things that I don't think will work. I want to understand how we address this greatest challenge of our time, how we provide clean energy to the entire planet and the prosperity that comes with it. Well, let's think about the first one we could tackle. Perhaps the biggest lever we have for decarbonization is electrification. Electrify everything. Electrify sectors that today are powered by thermal processes fueled by fossil fuels. Electrify transportation. Electrify buildings. Electrify manufacturing. Well, there's a couple of things that we need to think about. If we're going to do that, we're obviously going to massively increase our demand for electricity. By some estimates, electrifying those sectors would increase demand for electricity by on the order of 3 times or 4 times, a massive increase in the amount of electricity that we would need. And secondly, of course, it's only going to help us if that electricity is carbon-free. Well, let's think about how we produce electricity today. Let's think about what demand for electricity looks like across the course of a single day. If I look at electricity demand across the course of a day in the summertime, in the wintertime, there's some pretty striking characteristics. The first is there's an amount of energy that I always need. Doesn't matter what time of the day or night it is, there's some base load amount of energy that we need. So we'll call that base load demand. And then there's a piece that changes across the course of a day as people go about their business. And we'll call that dispatchable or load following electricity. So however I produce electricity, I'm going to have to be able to generate something that looks like this. What's my cost target? Doesn't make any sense to talk about producing more electricity if I don't have a cost target. Here's a really important one to remember. People are not going to pay a premium for electricity. People are not going to pay a premium for electricity. Prosperity is an immediate need. The consequences of that energy, whatever they are a long-term result. People massively underestimate the value of future events. So if we tell people they're going to have to pay a green premium to avoid a future event, they're not going to pay any attention to us. The cheapest way there is to produce electricity that looks like this is natural gas and coal. Natural gas is great if you have it, but it's distributed unevenly across the globe, and it's difficult to move around. So if you don't have natural gas, coal. Right now, coal costs about $100 a megawatt hour to produce electricity from. 10 cents a kilowatt hour. So that is going to be our cost target. So how are we going to do that? Well, we know that some of the cheapest electricity on Earth today comes from wind and solar. Solar electricity is far below $100 a megawatt hour. It's below $20 a megawatt hour. Some of it is as cheap as $10 a megawatt hour. So let's think about doing this with solar. 2013, the California Independent System Operator published what became, for the first time, what became known as the duck curve. And this duck curve tracks solar production and energy use across the course of a day. And what they showed is something that was really pretty obvious, and that is I get energy from solar when the sun shines. I get energy from wind when the wind blows. And those times of production don't necessarily correspond to times of use. So how am I going to deal with that? Well, I could store energy when I have it in times of abundance and use it when I have times of need. So let's think about that. We're pretty good at making batteries, right? We should be able to do that. Let's think about that. Well, intermittency in the context of the grid is actually a series of unrelated events that happen at very different time constants. Over very short periods of time, seconds to minutes, we have to deal with the fact that we use alternating current, and the frequency of that current has to be maintained. So as individual loads, as individual generations come on and off the grid, I have to maintain that frequency to a very tight tolerance. As I go to slightly longer time domains, say minutes to hours, I have another set of unrelated events that lead to intermittency. So this, for instance, is a real output from solar energy from a facility in Arizona across the course of a day. And you can see that at various times we have significant reductions in output from this facility compared to the average. So I'm going to have to deal with things that happen with time constants of minutes to hours. We can keep going further than that. Over hours to days, I have to think about other kinds of intermittency. Weather, for instance. I have cloudy days or a rainy week. This is wind output plotted with energy use from a facility in Texas over the course of a week. And you can see here that wind output mostly happens at night, energy use mostly happens in the day. So to deal with this intermittency, I'm going to have to store energy for hours or for days to shift it to when I need it. But we can keep going. We know that you don't get as much sun every day of the year. For everybody that was up early this morning, it was light at 5 o'clock. Solar insolation in Northern Europe is 5 times in the summer what it is in the winter. So if I'm going to use solar energy, I'm either going to have to massively overbuild this, or I'm going to have to store months' worth of energy across the course of a year. But let's keep going, because there's actually time constants even longer than that. We tend to think of hydro as dispatchable power. It's always there. I can turn it on and off whenever I want, but it's not. Hydro is just solar energy with a little bit of storage. The sun evaporates water, makes clouds, it rains, and I catch it behind a dam. 63% of Brazil's electricity comes from hydro. Brazil is currently in the middle of a decade-long drought, and hydro production is down by more than 70%. And how do they make up with that for that deficit? They burn coal. They burn coal. And over the same period of time, electricity prices in Brazil have nearly doubled. We've seen similar events with wind in Germany. 2020, 2021, wind speeds dropped and wind output fell by more than a quarter. And how did they make up for that deficit? They burned coal. And Germany has some of the most expensive electricity on Earth. Recently, the Royal Society conducted a study of wind output in the North Sea, a nice windy place. And they looked at wind output in the North Sea over a 50-year period. And they discovered that when you look at it over that long a period, there are years when wind output is down by more than 50%. So now, if I'm going to use storage to deal with these intermittencies, I'm going to have to store years' worth of energy for decades at a time. Well, let's think about the cost implications of this as well. It turns out that there's an inverse relationship between the time period I need to store energy for and what I can afford to spend on it. Very short periods of time, I can afford to spend a lot on storage. Longer periods of time, I can spend less on storage. One way to think about it is it's just how many times do I get to amortize that CapEx, right? If I'm doing storage over the course of a year, I get to amortize that CapEx once over the course of a year. By the time I get to 8 or 10 hours, things like lithium-ion batteries are too expensive. By the time I get to a couple of weeks, even things like iron-air batteries are too expensive. But we're going to have to do this for decades. And what about the scale? What about the scale of storage that I'm going to have to build out? This is the Tesla Gigafactory. This is the largest battery production facility on Earth in Nevada. Annual output from the Tesla Gigafactory stores 3 minutes of the US grid. It would take 1,000 years of production from the Tesla Gigafactory to store 2 days worth of US energy. So how is this going to work? It's not. Intermittent wind and solar energy is a tremendous way to make very cheap electricity. Very cheap electricity. And that has value. But it's a terrible way to make dispatchable electricity. If we're going to rely on electricity as a part of this transition, then our electricity is going to have to be reliable. We can't use intermittent sources that have intermittencies over this period of time uncorrelated. We've seen over and over again that when people try to do that, they inevitably run into shortages. And when they run into shortages, they burn fossil fuels to deal with those shortages. And it has an important impact on the price of that electricity. All right, well, what are we going to do? If we can't use intermittent energy sources, we're going to have to think of something else. We have only 3 energy sources available to us: the energy that comes from the sun, the energy that's stored in the earth as heat, and nuclear energy. We've seen the challenges with solar energy in whatever form. Are there other ways to do it? In 1980, it would cost you $50,000 to put a kilogram of material into space. Today, that number is $500, dropped by 2 orders of magnitude, and it continues to fall towards $100 a kilogram. And so all of a sudden, things like space-based solar that just a few years ago were lunacy are not so lunatic. And both NASA and the European Space Agency are looking into the possibility of space-based solar. Geothermal remains a massively underutilized resource. New technologies have relieved some of the limitations of geothermal. Long ago, you needed heat, water, and permeability. Now we know we can introduce permeability and water, and so a large fraction of the United States, for instance, is amenable to geothermal. There's a lot more we can do, especially by going to higher temperatures. Temperatures approaching 400 and 500 degrees Celsius. That'll require new technology for drilling. It'll require new technology for building and operating reservoirs. And then there's nuclear. In nuclear energy, what I do is I convert mass into energy. The amount of energy that's released when I do that is enormous. The conversion of a kilogram of mass into energy releases 25 terawatt hours of energy. The planet uses about 28,000 terawatt hours of energy per year. So the conversion of just a little over a ton of mass to energy releases as much energy as the whole planet uses in a year. There are 2 ways that I can release that energy, that nuclear energy. The first is fission, where I take a heavy nucleus and break it into 2 lighter nuclei, where the sum of the mass of the 2 lighter nuclei is less, a little bit less than what I started with. And the other way that I can do this is fusion, when I take 2 light nuclei and fuse them together into a heavier nucleus, where the mass of the heavier nucleus is a little bit less than what I started with. Nuclear fission today produces about 10% of the world's electricity. That number has been constant or slightly falling since 1979, since the time of the 3 Mile Island accident. After 3 Mile Island, the cost of building nuclear rose 5-fold to deal with the safety challenges of nuclear fission. And those are essentially 3-fold. Waste, the products of nuclear fission are radioactive for millennia, and so they would have to be stored for thousands of years. The products of nuclear fission are fissile and can be weaponized. And the third is that fission is inherently a chain reaction, so it is inherently susceptible to runaway reaction. Today, there are a number of new reactor designs that are under development. NuScale has a new reactor, TerraPower has a new reactor, reactors that are designed to deal with these safety issues, new fuel forms. But what's the cost entitlement? Well, we don't know because we won't build nuclear reactors. So we have a double whammy. We have a new technology that hasn't been deployed at scale, so I don't know what its cost entitlement is. And then the second thing is we stopped building reactors in the 1980s. So we've lost the muscle memory of how to do these things. We have to get back to building nuclear fission. It's almost impossible to see a universe where we do what we're trying to do that doesn't have nuclear fission. And then there's fusion. The attraction of fusion has always been that it suffers none of the limitations of fission. The products of nuclear fusion are radioactive for decades, so I don't have to store them essentially forever. They're not fissile, so they can't be weaponized. And it's not a chain reaction, so I don't have to worry about runaway reactions. So where are we with fusion today? Well, the old joke about fusion is that fusion's 30 years away and it always will be. But that's really not where we are today. That's really not where we are today. The fundamental challenge with fusion is how do you get those 2 nuclei to reach each other? The enormous repulsive forces of atoms stops that. There are essentially 2 approaches to doing that. One is to create a plasma where I strip all the electrons away so that 2 nuclei can find each other. And the second is inertial confinement fusion, where I use the enormous power of lasers to jam those 2 things together. The former is by far the most common, and the most common geometry for the vessel designed to hold that plasma is a tokamak, the familiar donut-shaped device that everybody has seen. Today, over 200 tokamaks have been built and operated globally. This is not some strange niche thing anymore. And a number of those have operated at very close to breakthrough energy and could have produced more energy than they consumed if people had just added more fuel. Today, there are commercial companies who are building full-scale reactors and who say that they'll put electrons onto the grid within 10 years. So nuclear fusion is a challenge, and it has always been a challenge, and I understand the sort of bad rep that it gets. But the potential is enormous, and we're a lot closer than people think we are. And we have to try it. We have to try it. We don't know. I said our mark was $100 a megawatt hour. We have no idea what the cost entitlement is because we haven't built one. And we'll never know what the cost entitlement is until we do build one. And so we have to work forward on developing these. It seems that there is no chance of doing what we need to do without nuclear energy, fission, or fusion. Okay, so now we've made electrons. Now we've made energy. What do we do with it? We distribute energy using the grid. The grid is often sort of an afterthought. People imagine it's sort of poles hung on wires. I create a generator of some sort, I attach it to those wires, and the energy moves through those wires to where it needs to go. That's not the right way to think about the grid. Remember that we use alternating current. That means if I'm going to use rotating machinery to produce electricity, and that is mostly how we produce electricity, that rotating machinery all has to be synchronized. It all has to be spinning at exactly the same rate and synchronized. In the United States, there are 25,000 generators distributed at 10,000 sites, and they all spin at the same rate and in the same time. It's extraordinary. It's absolutely extraordinary. The grid connects users and generators in a way that's completely different from any other dispatchable resource, in the sense that users don't schedule when they need electricity. You don't call a power company and tell them when you're going to cook dinner. Users don't schedule use, and generators don't store. Rather, the whole thing operates in unison. And neither are generators nor users isolated. There's not a power plant that powers your house. Rather, the whole thing operates in some giant mesh. It's really extraordinary that it works. We operate the grid by modeling supply and demand, typically a day in advance. And that modeling exercise used to be pretty straightforward. Generators were dispatchable and could be scheduled. The use of rotating machinery meant that there was an enormous amount of inertia in the system, which allowed me to stabilize the frequency of the grid. There was no cross-sector coupling. I didn't have to worry about the building sector or the transportation sector. Power flows were one direction. I could model the distribution grid simply as a load, and on and on and on and on. When I simultaneously grow and decarbonize the grid, all of that stuff goes out the window. Now, if I'm using wind and solar, I site my generators where the resource is, not where the load is. And that complicates transmission. It often means transmission happens over very great distances. And those transmission pathways vary with the weather. As I stop using rotating machinery to produce electricity, grid inertia goes down. As people start using distributed solar, I can't model the distribution grid as a load anymore, but rather I have two-way power flows, and on and on and on and on. It rapidly becomes impossible to calculate an exact solution for how the grid is going to operate. And people have to resort to an increasingly tenuous set of approximations. The modeling has to be done over 5 orders of magnitude in time and in distance. Recently, the City of Los Angeles partnered with the National Renewable Energy Laboratory to model what a carbon-free grid would look like for the City of Los Angeles. That study took 10 years and used 25 CPU hours of the NREL supercomputer to model just 4 static solutions. 4 static solutions in 10 years. We have to develop new ways to operate the grid. We have to develop new ways to model the grid. We have to build a device that we can work, that will work with intermittent and dispatchable resources together. So where does all this leave us? Well, electrification is absolutely the most powerful lever that we have to decarbonize thermal processes. It is absolutely the most powerful lever that we have. But we have to be realistic about what we can do. We can't build a grid with intermittent resource. We're going to have to use dispatchable sources of energy. And we're going to have to think about how we model the grid and how we operate the grid at the outset, not as an afterthought. All right, well, let's think about another big source of emissions. Let's think about transportation. The EIA says now transportation is about 8 gigatons of emissions, and that has roughly doubled over the past 30 years. And so has come a familiar call to end oil. Well, let's think about that a little bit. So first of all, ending oil is going to be challenging for a lot of modes of transportation. 6 of that 8 gigatons is light-duty cars and trucks. That can certainly be electrified. It's going to take time, but it can be electrified. Heavy-duty transportation, heavy-duty trucking, shipping, aviation rely on, need the extraordinary energy density of liquid fuels, right? So liquid fuels are going to be with us for a very long time. But let's just leave that aside. Let's never mind that. Let's suppose we could electrify all that. What would it mean to actually end oil? Well, oil, of course, isn't a single compound. Oil is instead an enormous mixture of compounds. And the nature of that mixture depends on where the oil comes from. So oil from 2 wells in 2 different locations would have a very different chemical composition. We separate those components in the refining process, essentially distillation. At the beginning of the oil age, in the late 19th century, the part of oil that was mostly used was the light part, kerosene for light, naphtha for cooking. And what we today call gasoline and kerosene was mostly wasted, often just dumped. More than half of a barrel of oil was just dumped. And so, almost from the very beginning, began a search for other things I could do with the rest of that barrel of oil. So, for example, candles in the first half of the 19th century were made from beeswax, not a viable source for large-scale production, and they were basically a novelty. By 1850, people were starting to extract paraffins from oil and using them to make candles, driving down the cost. When Europeans arrived in North America, they found that the indigenous people used a chewing gum made of spruce sap, and they followed suit, and that was what chewing gum was. Again, by the 1850s, paraffins from oil replaced spruce gum and became more popular than spruce gum. In the 1860s, petroleum jelly became used, and it was branded as Vaseline in 1870. In 1872, Thomas Edison patented wax paper. People discovered that pigments, colorants that wouldn't dissolve in water could be dissolved in some of the hydrocarbons from oil, and oil-based paints became a thing. By the time we get to 1885, there are 350 products from oil at market. Well, we saw that as we moved into the 20th century, the dominant use of oil became transportation, gasoline and diesel. Still, an enormous fraction of a barrel of oil was wasted, and the search continued unabated for other things that we could do with the whole barrel of oil. First came cracking, where chemists discovered that they could take large molecules that were too heavy to be useful for transportation and break them into smaller pieces. But the modern petrochemical industry really kicked off in the 1960s with the advent of steam methane reforming. In steam methane reforming, I take a hydrocarbon, mostly methane, but you could really use any hydrocarbon you want, and I convert that to a mixture of hydrogen and carbon monoxide. That mixture is both high energy and very reactive. And chemists can convert it to all sorts of things. You can turn it into liquid fuels. You can turn it into chemicals. In fact, the chemical industry produces just 7 intermediate compounds from the synthesis gas reaction: ethylene, propylene, butadiene, benzene, toluene, xylene, and methanol. And from that group of 7 compounds produces 6,000 compounds that undergird every single aspect of modern life. 65% of all of the fabrics that we wear come from oil. specialty polymers for biomedicine, agrochemicals and coatings, surfactants, sealants, adhesives, on and on. The list goes on and on and on. Everything from ballpoint pens to swimming pools, everything from refrigerants to dental adhesives. So look, a 42-gallon barrel of oil produces about 20 gallons of gasoline. It produces about 15 gallons of diesel and jet fuel. But every drop of that barrel of oil gets used. Every drop. And even more importantly, the economics of every drop of that barrel of oil depends on the economics of every other drop in that barrel of oil. There's no way I can take a little slice out of this thing and imagine that it's going to operate in a vacuum the way it did in context. If we're going to end oil, if we're really going to end oil, and never mind the fact that we're still going to need liquid fuels, if we're going to end oil, we better figure out how we're going to make those 6,000 compounds, or at least those 7 intermediates, at cost and at scale. Well, how am I going to do that? We said that syngas is the key. If I can get to synthesis gas, I can do anything. I can make fuels, I can make those intermediates, I can make almost anything when I get to synthesis gas. But if this is going to be zero carbon, if I'm going to be able to make fuels that I can use to fly jets and things like that, I need 2 things. I need a zero carbon source of hydrogen, and I need a zero carbon source of CO2. That is to say, if I'm going to burn it and put the carbon back into the atmosphere, it had to come out of the atmosphere in the first place so that there's no net addition of CO2 to the atmosphere. So how am I going to do that? On Mount Olympus in southwest Turkey, the rocks spout flames. Flames literally come out of the ground. This has been known since antiquity. Ancient sailors used the region for navigation. The original Olympic flame was lit from these fires. When people got around to looking what is the gas that comes out of the ground and burns, they discovered it's hydrogen. 5,000 miles away in Los Fuegos Eternos in the Philippines, flames again spout a foot out of the ground. And again, when we looked at the composition of the gas that was burning, we find it's 50% hydrogen. But the events that really stimulated the activity around so-called natural hydrogen happened in Mali in North Africa towards the end of the in 1980s. In 1983, villagers there drilling for water drilled a well that was about 110 meters, and it exploded. They assumed that they drilled into natural gas, and so they plugged the well. In 2014, people went back and unplugged the well to start extracting the natural gas, and very quickly discovered it wasn't natural gas. It was hydrogen, pure hydrogen, pure hydrogen. Since that time, 25 additional wells have been drilled around the region in the same reservoir, and hydrogen flows from all of those wells. Today, they use that hydrogen for electricity. In retrospect, it's really not that surprising that hydrogen would come out of the ground. The earliest reference that we can find in the scientific literature to hydrogen coming out of the ground is in the 1880s, when people observed it leaking from cracks in coal seams. There was a large discussion in the scientific literature in the 1970s and 1980s about the origin of abiotic oil. We knew for a long time there's a whole bunch of oil that doesn't come from decaying organic material. We knew that from isotopic analysis. So where does it come from? And the consensus was it was the reaction of hydrogen and CO2 in the ground to produce that oil. And around the world in various places, in Australia, in Brazil, in eastern North Carolina, these so-called fairy circles turn up. These are circular depressions in the ground, often near water, and from the periphery of those fairy circles, hydrogen is emitted. So we've known hydrogen comes out of the ground for a long time. So why does this matter? Why do I care? Hydrogen is pure reactive chemical energy. If I have enough hydrogen and it's cheap enough, I can do anything. Hydrogen is the Swiss Army knife of energy. I can make materials, I can make steel, I can make fuels. We even had fun playing around. You could make food at cost-competitive prices if your hydrogen is cheap enough. So how cheap is it? Well, estimates are that hydrogen at the wellhead from this natural hydrogen will be on the order of $1 a kilogram or less. It's extraordinarily low cost. And is there a lot of it? The origin of this hydrogen is still a little bit under debate, but most people, I think, believe that it comes from the reaction of iron 2 and water. If that's true, you're limited only by the amount of iron 2 in the Earth's crust. And that number is effectively infinite. Jeff Ellis at the United States Geologic Survey has estimated that the accessible resource may be as large as 1 trillion tons. 1 trillion tons of hydrogen is enough to power all of humanity for thousands of years. So there's a lot of work left to be done. How do we get it out of the ground? How do we find it? All of those kinds of things. But make no mistake, this is the most important discovery in energy in our lifetime, and probably the most important discovery in energy in our children's lifetime. Another really interesting aspect of geologic hydrogen is it's a way to make that load following or dispatchable power. Today, we make most of that load following electricity by burning natural gas in turbines. I can also burn hydrogen in turbines, or I can convert hydrogen directly to electricity in fuel cells. So that load following component becomes possible with hydrogen, zero carbon. I have to move it. There's about 2.5 million miles of natural gas and oil pipeline in the United States. There's about 1,700 miles of hydrogen pipeline in the United States. That's because some kinds of steel react with hydrogen in a process called embrittlement. There's new technology that's needed to understand how we can stop that embrittlement process. Or we need to build out new infrastructure with new materials that aren't susceptible to embrittlement. There's work to be done, but these are problems that can be solved. Well, if I've got hydrogen now, effectively an infinite amount of hydrogen at a very low cost, the other thing I need is carbon. And we said if we're going to use this process, at least to some extent, to make fuels, then that carbon has to be zero carbon. It has to come out of the air. How are we going to do that? Well, we know that there's already a lot of technology being developed, companies operating to extract CO2 from the atmosphere for sequestration, to just store it. But that process today is still far too expensive. Carbon capture directly out of the air is on the order of $500 to $1,000 a ton. Just for context, if you have to pay $100 a ton for your carbon to make fuels, it adds about 85 cents to the cost of a gallon of gasoline. So if I have to pay $500 a ton, I'm already out of range before I do anything else. So the costs of carbon capture have to go way, way, way down before we can use it as a reagent. I can also use biomass, right? Plants extract CO2 from the air autonomously using sunlight as an energy source. And I can convert this biomass into syngas, so I can go this route as well. But if I'm talking about terrestrial plants, then I compete with other applications for valuable resources. I compete for land, I compete for water, I compete for fertilizer. So that there's important societal discussions to have about how much of those scarce resources we want to direct towards the production of liquid fuels. So work to be done, but incredibly optimistic. Let's come back to this business of energy equals prosperity. We showed the growth in prosperity across the course of a couple of centuries in a single place. We can also show this relationship by looking at prosperity across the 200 countries on the planet. So if I plot energy versus prosperity, for those of you who are still paying attention, that's a log-log plot. That's a log-log plot across 3 orders of magnitude in both dimensions. And that's a damn straight line. Energy is prosperity. But here's some more bad news. If energy is prosperity, prosperity induces a set of behaviors that produce more emissions. So what do I mean by that? Well, as I increase in prosperity, the first thing I want is shelter. And so I build shelter out of steel and cement that together are responsible for 15% of emissions. And so in just 3 years, between 2009 and 2011, China used more cement than the United States used in the last century. There's nothing special about China. This will happen to every country as they achieve prosperity. As people acquire wealth, they want mobility. That correlation is so strong that economists use the number of cars in circulation in a population as a measure of the size of middle class. As people acquire wealth, They want calories. And in particular, they want meat that's responsible for 20% of global emissions. As people acquire wealth, they want air conditioning. Air conditioning is about 10% of global electricity today. 90% of homes in the United States have air conditioning. In Mexico and Brazil, that number is 16%. In India, it's 5%. And on and on and on. Look, I don't want to come off here as pessimistic. I'm not pessimistic. I'm incredibly optimistic. I don't know how anybody could walk around this place and look at the technology that's on display, talk to the inventors that are here, talk to the founders and the funders, and not be optimistic, right? You have to be. You can't possibly not be optimistic. But it's important that we have clear eyes and understand the magnitude of the challenge that's in front of us. There's no sugarcoating this. There's no sugarcoating this. And in fact, the scope and scale of the problem sometimes leads people to funny places. So there's a reaction that you'll sometimes see where people will say, oh, it's not hard, it's easy. There's easy ways to do this. And deployment of those easy ways to do this are being frustrated by evil governments or evil corporations or something. It's not true. It's not true. There is no easy button to push here. It's hard work, and it's going to take a long time. But remember, too, that there's another reaction that sometimes comes up, and that is to say, I'm throwing up my hands. The problem is so hard, it's insolvable. And that's wrong, too. It's not insolvable. It'll take time. It'll take work. But look around you at the group of people in this room. If we work together and keep doing what we're doing, we absolutely can solve the greatest challenge of our time, to provide energy and the prosperity that comes with it to the entire planet. Thank you very much.